We have here four of an independent variable, which is driving condition. Our dependent variable here is the likelihood, the probability of a collision while merging. We have four different levels where either the individual drives alone. The passenger condition, you have a chatty passenger right next to you. You have a video phone condition where you're on the video phone with somebody else, and you have a cell phone condition where, as the fourth group, you have somebody on the cell phone who you speak. It's now 4 years I'm teaching this class, and it will, whenever I look at this graph, always be a mystery to me why cell phone would be more dangerous than video phone. But maybe one semester somebody can explain this to me. But nevertheless, so we have here four different groups with four different probabilities of likelihood of colliding with somebody else. So what you could hypothetically do, you could be interested in drive alone versus cell phone, which seems to be quite different. You can do individual comparisons. That's one way to do that. But we will discuss a reason why this is not advisable. Because when you do that, you have with each comparison, you have an alpha of 5%. So when you do a hypothesis test comparing driving alone versus driving with a cell phone, you're basically comparing this, accepting an alpha probability of rejecting something you shouldn't reject with a probability of 5%, which is a lot, particularly when you use multiple comparisons, because if you have four groups, you're looking in essence at 6 comparisons. Just think it through, because you need to compare all the groups. If you have 3 groups, you have group A, B, and C. You're comparing group A versus group B, group A versus group C, and group B versus C. So that's 3 comparisons. If you have 4 groups, you have 6 comparisons. So the problem with this error is that this error will then increase as well. It increases essentially exponentially with the number of groups. So when you have 3 groups or 4 groups, you come with 3 groups, you're up at 14%. With 4 groups, you're up at 27%. If you have 6 groups, you're basically more likely to commit the type 1 error than not. So that's essentially, that's problematic, as you can imagine. So the reason why you will basically refrain from doing multiple t-tests is that it's just too many tests. You increase your probability of type 1 error, and your alpha is just through the roof. Therefore, you are now expanding this a little further. So you come, I don't like the analogy with the Swiss Army knife, but essentially you have just more groups, and you're spreading your hypothesis out amongst all those groups. And essentially you come now to the 3rd level where you have 3 or more samples, 3 or more levels of your independent variable, creating 3 different samples that you're comparing. And the null hypothesis here is basically that you have one grand mean, and that there's a difference between at least one of these means from the grand mean. And you're analyzing this, calculating a so-called F. And this F is basically a ratio between the variance between the groups, which basically, when you look here at this graph of the collision while merging, you have here 2 variabilities on this graph. One is basically the variability within that group. So this is a variability that is basically based around that mean of that group, assuming with a certain sample size within that group that there's a certain variability that you will have in your estimate based on that variability between those individuals. But you also have a variability between the groups. So if you would assume there to be a mean of these 4 groups, each of these mean estimates would differ deviate from that grand mean. And that deviation is nothing else but a variance, right? So you have an individual deviation from a grand mean. Squaring this gets you to the sum of squares. Dividing it by the number of groups, -1, gets you a degree of freedom of the groups, and there you are at the variance. And this is the variance that we will calculate today, and this is the variance that you need for the estimation of your F. So you're quantifying variance between groups in the numerator and variance within groups in the denominator. So it's the difference amongst the sample means divided by the average of the sample variances. So it's the differences between the group means. So that's the mean of means. That's the estimate of the population variances based on the difference within the sample distribution, within the sample distributions from the mean. If you are now focusing, so we're doing today a one-way between groups and over. Just in terms of nomenclature, if you have one dependent, you always have one dependent variable. You have one independent variable with 3 or more different levels. It's a nominal variable, so it has different levels. If you have now more than one independent variable, we're talking about a two-way between groups and over. Within groups is a different ANOVA, which is an ANOVA which we will do on Wednesday. This would be on Wednesday, we're discussing a one-way within groups ANOVA. This is an ANOVA where you have the same participants undergoing each level of the independent variable. It's basically the ANOVA equivalent to the paired sample t-test. In essence, it's just more than 2 time points. So it's also called a repeated measures ANOVA. But more about that on Wednesday. So these ANOVAs have 3 assumptions that need to be made. First assumption is that the samples are randomly selected, that you're not predefining those samples based on a specific assignment, but you have independent samples, independent levels of independent variable. Then you have also you need to assume normally distributed samples, which is with the small sample sizes that we're dealing with is like something we cannot safely assume. But for the sake of this teaching example, we assume normally distributed sample, and we need to have something that is called homoscedasticity. If you remember the independent sample t-test and paired sample t-test formula in Excel, we had already a bit of an exposure to homoscedasticity. We had, you remember when you put it in a formula builder, you have 1 for paired, 2 for paired samples, not 1 for paired, 2 for independent samples with equal variance, which is homoscedastic, and type 3 was independent sample t-test with unequal variance, which is heteroscedastic. Homo means same or equal, whereas hetero means different. So homoscedasticity, excuse me, homoscedasticity talks about equal variance between the groups. That means that the variance is somewhat comparable between all the groups, all the levels of your independent variable. And that essentially should not exceed 20%. That's the rule of thumb. Okay. Any questions on that? On the assumptions? So random sampling, normal distribution, and homoscedasticity. The 6 steps of hypothesis testing are just the same as they always are. We're identifying the population, we're identifying the distribution, we're making our assumptions. We state a null and research hypothesis, and we determine the characteristic of the comparison distribution. We determine critical values. We calculate the test statistic, and we make a decision. So when we think of that F that we're calculating, this is our comparison distribution. So this F distribution, essentially, we are comparing against an F distribution. The F distribution is as opposed to the normally distributed T distribution, and the normally distributed set distribution is now a unimodal right-skewed distribution with a cutoff at and critical F that is to be determined based on the degrees of freedom in either the numerator, which is the number of groups, the degree of freedom of the groups, or the degrees of freedom in the denominator, which is the degrees of freedom in within the groups. And we will learn how to calculate it in a second. So this is our critical value. That's how we determine our critical value. And then we're basically making a decision based on the calculated F and the critical value and the calculated F. We will either reject or accept the null hypothesis, and the null hypothesis will be that these groups are not different from each other and from the grand mean. Good. Okay. So we will calculate, we will do today example 12.1 in your book, which essentially is the so-called dictator game. So the dictator game is basically a sociological experiment where 15 societies all over the world have been investigated. The dictator game basically was using a sum of money that was equal to the daily minimum wage of that society. The first player had then the choice to either keep all the money or give a portion to it to the other person next to him. The proportion of money given to the second player constituted a measure of fairness. For example, it would be considered fairer to give the second player 40% of the money than to give him or her only 10% of the money. So we have here the estimates. The estimates of this fairness scores for four different societies. So we kind of see a little bit of a trend towards more fairness in industrial countries, a notion which may be debated, but nevertheless, so we see a little bit of a trend towards one group favoring over the other. So now we, in step one, we basically determine that we have four populations. We have our assumptions met. So we assume it's normally distributed. We assume random sampling. And we assume homoscedasticity. Good. So now our comparison distribution here is the F distribution, as we know already, because the independent variable of society, that's our independent variable, is basically represented as four different levels. So in step two, we are phrasing our null and research hypothesis. Well, the null hypothesis is that people living in societies based on foraging, farming, extraction of natural resources, and industry exhibit on average all the same fairness behavior. So one possible research null hypothesis could be M1 equals M2 equals M3 equals M4, right? So that's our null hypothesis. And then the alternative hypothesis basically is now that at least one is different. At least one is different. Now, next we need to quantify the characteristic of the comparison distribution. The degrees of freedom between is calculated as the number of groups minus 1. Example. The degrees of freedom within is calculated as the group-specific degrees of freedom summed up. That gives us the 2 degrees of freedom. And that's easy, right? It's like the degrees of freedom between is now 4 minus 1. So that's 3. And degrees of freedom within is basically, so we have here 4. That's 4 minus 1 plus 3 minus 1 plus 3 minus 1 plus 3 minus 1. That sums up to a total of 9. That's 2, 2, 2. That's 6 plus 3 is 9. So degrees of freedom between, degrees of freedom within. So now in the next step, we'll basically determine our critical value. So step 4 is the determination of our critical value. Critical F. So we have degrees of freedom between of 3. So we have this F-score table labeled. So there's a lot of stuff going on in the grid. So we have degrees of freedom in the numerator. It's basically the columns from 1 to 9. Degrees of freedom in the denominator is basically the rows. And these rows are substratified into 10, 5, 2.5, 1, and 0.1. That's the alpha. So if we have degrees of freedom in the numerator of 3, we go all the way down. And we find here degrees of freedom in the denominator of 9, which is our degrees of freedom within. We're finding at an alpha of 5%, we find our critical F at 3.86. Right? 5%, 9 degrees of freedom within, 9 degrees of freedom within, and 3 degrees of freedom between. So now our critical F is 3.86. And then step 5, and that's the tricky one, as you can imagine, this is calculation of the test statistic. So again, here's the depiction of this unimodal right-skewed F-score distribution, which is basically here with 3.86. Everything exceeding 3.86 is now an alpha of 5% or less. So now we're quantifying now the overlap between the respective variances of these groups. And by getting those aligned as a ratio between the variances within, as a ratio of the variances within, gets us now an F. And this is a really good depiction of what I'm actually saying here. So these are the four different societies with entries within the society. You have the respective entries within the society. They are basically differing amongst each other in terms of these mean estimates. And we have here the black line basically depicts the so-called grand mean. That's the mean of means. But we additionally, and the arrows, the group mean for the grand mean, basically indicates the deviations from this grand mean, which basically is then being used for the degrees, for the quantification of the variance between groups. The variance within groups is calculated as we always did it within the samples. We're calculating the group mean, You're calculating the difference between the group mean and the respective individual score. Gets us the variance within. So the overlaps between these variances is basically now showing what are differences between the groups and the differences to the grand mean. And the so-called source table is really how you will present this in step 5. So we've talked about that you may not have to ever code anything in R or do anything in SPSS. That's possible, not very likely, but possible. But what you certainly will have to do, that's even more likely, is that you will have to integrate the so-called ANOVA source table. And the ANOVA source table basically has your labeling of the source of between, within, or total. And it consists out of 4 different components. It's here the sum of squares constituting of sum of squares between, sum of squares within, the sum of squares total. Then we have the degrees of freedom. Then we have the corresponding variance, which is basically calculated as sum of squares between or within, divided by degrees of freedom between or within. Remember how to calculate the variance when you calculate the standard deviation. You calculate the individual deviations from the mean, you square these deviations, you sum these squared deviations up, you get the sum of squares. You're dividing it by the degrees of freedom, you are at the variance. You're doing the same thing here. You have a sum of squares between, sum of squares within. You divide it by the degrees of freedom between or within, and you get to the variance between or within. The ratio between variance between divided by variance within is then the F. And that's your test statistic for an ANOVA. It's simple, right? It's not terribly different. Okay. So let's copy this source table over. Let's copy it right here. Doesn't matter. Let's make this always more. So now we have the source table again. Sum of squares, degrees of freedom, and MS. So degrees of freedom we know already, right? So we have degrees of freedom between, that is 4 minus 1, so that's 3. Degrees of freedom within, that's 3 plus 2 plus 2 plus 2, that's 9. And degrees of freedom total is 9 plus 3, that's 12. That's how simple it is. So next. Now it's getting a little trickier because now we need to we need to calculate the grand mean. So keep this in mind. If you take all these individual entries and you calculate the mean, you get the grand mean. So the first thing, and that's the most, it's not the most annoying thing, but it's the second most annoying thing, is to basically go and bring your scores into what we call a long format. And you know already, you remember the long format. This is basically, you click on the cell. Let's take it O. You click on the cell on O2, and you click on paste special. And when you click on paste special, you can do transpose. That's how it will transpose your values. Transposing is basically bringing it from a wide format to a long format. Then you just have to calculate, pick the society, the corresponding society, and just fill it for all those 4 entries. You do the same for farming. You copy it, you go on 06, you go on paste special, you go on transpose. You take farming, you spread it out over those 3. Do the same for natural resources. Transpose. Okay. Oops. Not good. And then lastly, we take industrial. We take industrial. I calculate society score, you just label it. And that basically gets you now all this data in the long format. Only thing you need to do is to calculate now the average. That's just the average of all these individual scores. Simple, right? Next thing we need, that's a little trick here. We need the so-called group mean. And that group mean we need for that reason, because now we also want to quantify the variability within. So we need to calculate the group mean for each of these entries for that group they're in. And that's a little annoying. That's the most annoying thing. So we have, we're calculating now on, we're calculating the average for all these 4 entries for foraging. Caveat, we need to lock it in with the $sign. And then we basically just copy this all over previous 3 entries. We do the same for farming. Again, we need to lock it in. We just copy it over all the other 2. Do the same for natural resources. Again, we need to lock it in. And we do the same thing for industrial. And again, we need to lock it in. So that gets us the respective group means propagated for each individual score. Of note, this gets us to the next point, and this is essentially the calculation of all individual entries. So here we have, how are we going to do this? Let's copy the whole thing over. We can calculate now. Can kind of adjust this. So now we have the formula here. And we see already the formula. Oops. Oops. So we have now our 3 different sum of squares that we're calculating. So we have the individual between groups sum of squares. That's the sum of each individual mean minus the grand mean. So all of these entries for mean minus the grand mean. It's important to keep this for each individual scores, because otherwise you would be altering the degrees of freedom. That gives you a wrong result. So you need to propagate this for each score. So if that's pretty much simple. So we're doing now m minus gm squared. That gets us the between groups sum of squares. So this is this m, oops, bracket, this m minus the gm logged in, obviously, squared. We just need to propagate this all the way down. So now summing this up gets us the sum of squares between. So this is the sum of Q14 to Q2. It's 461. So now the next is x minus m squared. That's a little simpler because that's just this score minus this m squared. So now this is the sum of squares with m. So the sum, the R14 to R2. It's 167. With x minus gm squared. It's not this x. With a bracket minus the gm. Again locked in. Oops. Squared. That's the sum of squares total. Which again makes sense, right? It's like when you review the formula is S2 to S14. When you think about it logically, so you have sum of squares between the groups. So that's the variation of each individual n to the grand mean. Then we have the individual x minus the m, which gives you an within group variability. Squared gives you the sum of squares within the groups. And then you have the x minus gm, that is the total sum of all variabilities. So if you want to bring this now to your table, you have the sum of squares between, that is your 461. The sum of squares within, that's the 167. And the sum of squares total is 629. Of note, sum of squares between and sum of squares within adds up to 629. So if you have two of these given, you can derive arithmetically the third one. Simply, right? Equally with the degrees of freedom. Same concept. So total is always the sum of between and within. And when you utilize the same approach now to calculate the actual variance, it's just like it is with the calculation of the standard deviation. Same concept applies here. You just calculate the sum of squares that we have, and you divide it by your degrees of freedom. So your variance between equals 461 divided by 3, 153. The variance within is 167 divided by 9. So that gives you 153 and 18.6. Your F is now variance between divided by variance within. Gets you an F of 8.27. So now comparing an F of 8.27 and critical F of 3.86, we are exceeding our critical F. Therefore, in step 6, we can say we're rejecting the null hypothesis. So m minus gm for each individual square gives you the deviation, squaring those squared deviations. The sum is the sum of squares between x minus m, so individual score minus the means for each individual score squared gives you the sum of squares within. And the total is the individual x minus the so-called grand mean, gets you the total variability of each individual entry and is also the sum of squares between and sum of squares within. And this arithmetic dependency is very important also. So we reject the null hypothesis because it's here, right? So that's the depiction. It's like it's exceeding the cutoff. What's also important is this association here. So, okay, let's get to the later. Okay, so here the sample variances. So you need to calculate the sample variances because we are assuming homoscedasticity, right? So if you are now looking at this, let's put this a little over. If you have a sample variance, you have x minus m gives you the individual square deviation, just like calculating the standard deviation, same thing. So you have within these 4 entries, you have your information for your variance of the foraging group. So calculating the sum of these 4 entries, dividing by the degrees of freedom of that group, which is 4 minus 1, which is 3, gets you the variance. That's the variance within the group. That's the within group variance. If we do the same here with these 3 guys, and dividing it by the degrees of freedom, which is 3 minus 1, it's just 2, we get a degree. We get a variance of 19. Summing up x minus m squared divided by 3 minus 1 is 2, and the answer is 3. Is this divided by 3 minus 1 is 2, that's 13. So why we're doing that? Because so this is within groups variance. That's basically the variation of within these groups. So we say that there shouldn't be a deviation more than 20%, which essentially is true for these 3 groups. These are a little bit outliers, but let's, for the sake of this being a teaching example, let's leave it at that. But hypothetically, it shouldn't exceed 20%. That's the rule of thumb applied by many statisticians. So you have these variances within those samples calculated. So you should also compare those and make sure that they are somewhat homoscedastic. So once you compare this to the critical F, you basically know whether you're rejecting the null hypothesis or not. And then you do, just like with the t-test and the z-test, you're calculating effect size. The effect size here is a little bit different because the emphasis is really like, how much overlap do you have between the variances between the groups, and how much do the groups actually differ from each other, right? That's why you're calculating the variance between the groups, between those group means, as a fraction of the variances within the group. So you're comparing this variance between those 4 groups over the sum of the variances here within those groups, because this gives you an estimate of how much overlap you have between those groups. So if you want to quantify now, but the emphasis is really on the difference between these means from each other and from the grand mean. So that's why the effect size in an ANOVA is basically quantifying the proportion of variance that is basically explained by the between groups variance. Because that's really where the effect of these differences between the levels of the independent variable goes into. So you're quantifying the proportion of how much of the variance is attributed to the between groups variance. So this is simply done by calculating the R squared. And this is basically sum of squares between as a fraction of total. And the R squared here is 73%, 0.73. That means that the weight of the variance and the total variance is really on the variance, the differences between the groups. That means that this is a very large effect size. And the conventions are presented right here on the next slide. So you have 0.01 as a small effect size from 0.01 to 0.06, 0.06 to 0.14 is medium, and greater than 0.14 is large. So we have with 0.73, we have a very large effect size. So I have also included 16. Oh no, it's actually a PDF. A PDF that shows you an alternative. So firstly, R squared is also synonymous with eta squared. So on the quizzes, no eta squared. Also, there's omega squared. Omega squared is an alternative calculation of the degrees of the effect size, incorporating the information of the degrees of freedom. So basically, it lowers the sum of squares between, so that proportion that is being put as a weight on the sum of squares between, but taking into account the degrees of freedom between and also the variance with them. So basically it diminishes the effect size and it kind of corrects it for the number of groups and for the variance within those groups. Because both may have effects on the total variance. So you're diminishing this from the estimate of the total variance, thereby getting a little bit more of a realistic estimate with many groups and with large variabilities. But we're not going to go too deep into this topic. Good. So that's effect size. Any questions? No. Good. So after you did an ANOVA, what can you say after you did an ANOVA? The null hypothesis is that all the means are the same. The research hypothesis is that at least one is different. If you have a significant F, and you know your F for all the groups exceeds the critical value, you know that the variability is not entirely overlapping and that at least one of those groups is different from the other ones. And so next, you may want to find out which one, but you need to find it out in a way that does take into account that you do multiple testing at this point. Therefore, you need to do multiple testing in a way that kind of penalizes your comparisons for that multiple testing, because you have an inflated type 1 error, so you need to take this into account. Two ways to do that. One is the Tuckey honest significant difference test, Tuckey HSD. The second one is the Bonferroni corrected multiple comparisons p-value. So that's these are the two approaches that can be used. The second one is if you have an a priori blind comparison. A priori means that it's a thought experiment before you actually conducted your analysis. That means you've thought about it before, and you have formulated it before, and you have expressed it before. That means you have planned it before you actually thought about doing the analysis. So you basically all planned analysis or comparative analysis will be the second reason why you do group comparisons. Yeah. So the Tuckey honest significant difference test is essentially calculating an HSD. So the HSD is basically an M minus M2. So that's the comparison, right? So we're doing M1 minus M2, dividing it by the SM, which is basically standard error of the mean, which is basically our variance within, total variance within divided by the n square rooted. So if we do this for our example, let's copy this over. If we do this for our example, we essentially get here so we have here an effect size. Now we're doing post hoc. Now we do HSD. We have an SM, which is basically MS within. So that's the variance within divided by our N, which is 12. Square rooted. So we're getting here an SM of 1.24. They calculate. Okay, so HSD is M1 minus M2. So we're doing foraging minus farming. We do foraging minus natural resources. Let's just do two examples. Oops, too much. So we have now averages. Let's do these two examples. Let's see what there's M1, M2. So foraging is the average between those four. Those values. M2 is farming, that's average. This of natural resources, so average of, okay. So now if we want to calculate HSD, it's basically M1 minus M2 divided by our SM. So minus 1.4. So these are obviously, you can set absolute. They basically have 1.4 and 11.3. So now this can now be calculated and compared to the so-called Q table, because this HSD is basically the so-called Q. And this Q, if you have two levers, if you have four levers, in the within groups of degrees of freedom are here, within groups degree of freedom are 9. We're basically looking at critical Q with an alpha level of 5% of 4.41 or 5.96 if you take 0.1% or 1%. So for our case here, foraging versus natural resource, even after adjustment for multiple comparison, does result in a significant difference. whereas foraging minus farming does not. And this can obviously be done, can be done then for all differences. Good, so that's Taki's honest significant difference test. The other test is the so-called Bonferroni test. That basically gives you a stricter critical value for every comparison. So you basically you're diminishing your critical region, so you're smaller the critical region from 5% down to whatever the new Bonferroni corrected alpha is, which is basically dividing your alpha by the number of comparisons. So if we have 4 groups, we have 6 comparisons, so that would be 5% divided by 6. So that basically gets us here to 0.008. So that would be our threshold for all comparisons. And then you basically do multiple comparisons, comparing each individual group by basically using the same t-test approach that we used in the past, but your critical value that you would use to reject the null hypothesis is then adjusted to be 0.08 rather than 0.05. Good. Any questions on that? Okay. So, ANOVA. Again, so we have 4 different groups. Just as a recap. With 4 different groups, we go in step 1. We are quantifying the 4 populations that normally distribute. We have done random sampling and the homoscedastic. So testing a little bit further down. Step 2, we're phrasing our null hypothesis that all 4 means are identical. And also we are expressing our alternative hypothesis that at least one of these means is different. Degrees of freedom calculated as the number of groups minus 1 for the between groups. Degrees of freedom, that's the respective sample size of each group minus 1 each. Summed up, that gives us the degrees of freedom within. Degrees of freedom between and degrees of freedom within will allow us to look up the critical F. And the critical F is found in our F-score table, where we basically have degrees of freedom in the numerator as columns, degrees of freedom in the denominator as rows, with our example of 4 societies with altogether 12 participants. We have a degrees of freedom between of 3. We're looking for 5% p-values or 5% alpha. That would be the second row in each respective corresponding line. So therefore, we're going to a degree of freedom in the denominator that corresponds with our total number of participants. It's 12 participants in total. It's 4 groups. Oops. It is 9, it's 13 participants in total minus 4 groups. So 4 different degrees of freedom, summing up to 9 as degrees of freedom. We're going to degrees of freedom in the line corresponding with degrees of freedom in the denominator 9. We're finding 5% in the column for 3 degrees of freedom in the numerator, which corresponds with 3.86. So 3.86 is our critical F. Next, we just need to basically populate our ANOVA source table. Know how to do that, know how to read it. So you have the source shown in column 1. We have between, within, and total. The sum of squares in column 2, where we have the between groups sum of squares in the first row, within groups sum of squares in the second row, and the total sum of squares in the third row. Degrees of freedom between is 3. within is 9, the total is 12. Dividing now the sum of squares divided by the degrees of freedom is now summing up to the variance. So it's calculated now as the variance. The ratio between variance between and variance within is now the F, which gets us to an F of 8.27. And based on that, we're rejecting the null hypothesis. Keep in mind how to calculate these respective sum of squares. Where basically the between group sum of squares is calculated as the individual mean minus the grand mean. So that's the deviation of the individual group mean from the grand mean. Calculated for each individual score to preserve the degrees of freedom. When you have the within group sum of squares, it's basically each individual x minus the individual m, again for each entry in each group, and then summing them up for every single entry. The sum of squares total is basically now x minus gm for each individual x squared. That's the sum of square total. So that's the total variability of each individual score. This is then populating the source table. The ratio between variance between and variance within is then our F. It's to be seen in distinction to the effect size. So that's the ratio between variance plus variance with between over variance within. So that's the ratio between these two variances. But the sum of both variances, that's our total variance, our total sum of squares. Calculating now the sum of squares between, which also only constitutes the variance of each individual group mean from the grand mean, as a fraction of the sum of squares total of each individual x from the grand mean, will get us an estimate of how much of the variance is attributed to the variance between the group means specifically. So that gives us that proportion, and that's the effect size. And then you have two different ways how to calculate these multiple comparisons. Once you know this is significant, once you know you're rejecting the null hypothesis, or you had a pre-planned a priori comparison that you had planned, then you will basically move into post hoc testing, which you do either with a TACI HSD, a TACI honest significant difference test, calculating your Q by calculating the group differences divided by a standard error of the mean, pretty much. So it's the variance divided by your sample size square rooted, gets you to that as m. The calculation, the calculated Q, you can then compare to the Q table, which you have in slide 35. Alternatively, you can also do a t-test with a new alpha level, which basically comes only corrected, which means the alpha is basically divided by the number of comparisons, and thereby smaller. So you have smaller tails, and you will only reject the null hypothesis if it is actually as extremely different as those smaller tails. Any questions? Well, if not, that's all I had for today. We made it through and over. So it's a fun test. It's fun to calculate. Please make sure to review and understand the respective calculations. I'm not saying you're going to have to do an ANOVA, but some fractions and some fragments of that will need to be known for the quizzes. You will not need to go through all the calculations, but you will need at the very least need to know the associations that you're looking at in the calculation of a source table, for example. And you will have opportunity also to look at that in the homework, which also has some examples to that extent. What else? Yeah, next time we're gonna do on Wednesday, we're gonna do an over within groups. That's basically when you. So for the dictator game example, it would be literally people from foraging societies moving to industrial societies and playing the game then 10 years later. That would be kind of the setting you're basically looking at. So you have repeated measures at different levels of the independent variable of the very same participants. So you're basically doing a paired sample t-test with the same participant over different levels of the independent variable, which is beautiful, because what happens is, if you look at this, I can speak about this first. Since you're still mind for a couple of minutes. So we have here the source table, and we have now where is it? We have the source table now supplemented with an additional variance estimate. And this is the variance of the subject. Because you have variability not only between the groups and within the groups, you also have now variability within the subject. And what happens now if you add this as an additional variable in here? You can actually just a little teaser. No, I don't have it. If you add this as an additional line, so the total will still be the same, because you still have the same group variance overall. Individual entries, they're all differing from the grand mean. But you have now an additional line in between here, which is the variance of the subjects. And you will be able to subtract the substance variability from the within variability, diminishing the within variability and attributing some of the variability to the subjects, because there are differences between the subjects. Thereby, the calculation of the F, the overall comparison between the groups, will be larger because you're taking out the subject effect. That's actually pretty brilliant, and I'm looking forward to joining you on Wednesday. Okay, so that's all. Have a nice evening, and see you on Wednesday. Hi.
For class, I came straight from an appointment. That's why I was taking this on my phone.
Yeah.
I
am.
Thank you.
Hi, awesome.
Anna, yeah.
Awesome, thank you so much.
Sure. Thank you. Bye-bye. You there?
I think. In my head, you go very well. I was like,